Alrighty, this week we're continuing our talks on work and energy. Do go to the Olathe schools that I put on the Google Class weekly lesson. It's the week one. It's all about work and energy. Professor Dave, a video on there. Professor Dave does a pretty good job of explaining the difference between these kinds of energy. So this is going to take a couple videos to do. It's kind of a lengthy PowerPoint, and I can only do 15 minutes at a time. So let's get started about energy, which is the ability to do stuff. So we're talking about mechanical energy. We've talked about chemical energy in batteries, chemical energy of the body, to turn that into do mechanical work, to actually making stuff move around. So it's the energy due to the position of something or the movement of something. We have two kinds of mechanical energy we're going to talk about. One is kinetic energy, energy of motion, and the other is potential energy. Specifically, we're going to talk about usually gravitational potential energy, the energy something has due to its height. But there's also another kind of mechanical energy called elastic potential energy, which is stored in a rubber band, a bow, and all kinds of things that are elastic. Okay, things that are elastic, they can stretch and they go back to their normal size when the stress is taken off. And of course, the unit for energy we're going to use is the joule. So we're not going to be working in American units. We're going to largely keep it metric and Newton meters, kilograms for the entirety of this. So we've got your elastic potential energy caused by something stretching a spring or a rubber band. Chemical energy, energy stored within a substance, like in a battery within your body. We're talking about tissue in your body can be used, can be converted into energy. And of course, we have the gravitational potential energy, which is largely what we're going to be talking about, and only a little bit about the elastic potential energy. So the gravitational potential energy is due to the height. So to find work, it's force times distance. Well, the force, you have to find the work done to lift something. Well, the force to lift something is your mg. That's your weight. Times your height over here, the distance traveled in the same direction. The work done is the same as the gain in potential energy. So that's a pretty easy thing to figure out the relationship between work and potential energy, because the work you do on this thing is equal to the potential energy, or the work done on it is a better way to describe that. So the more height, the greater potential energy, or the less mass, the less potential energy, or the more mass, the more, because you have to do more work. So for an example, 50 kilogram boulder, 3.5 meters, well, it's 500 newtons roughly, times the 3.5 off the ground. Remember, we're doing the G thing. Use 10 for the quickie or the 9.8 for the exact. Okay, so here they're using 10 meters per second squared. This is the quick and easy way to do it. So it makes that 500 times 3.5, which is 1,750 joules. So the work done on this boulder was in fact 1,750 joules, which is the same as the gain in potential energy on that thing. Now, if gravity pulled this thing off, gravity would do 1,750 joules of work, pulling that down clear to the ground, and right before it hits the ground, it would have 1,750 joules of kinetic energy, but that's where we're going in shortly. Alrighty, so which ball has a greater potential energy? It's the high one. Very good, it's the high one. So being higher, it can do more damage on something. It's a potential to do more damage than something that's not quite as high as another object. So it's 5,000 joules for the high one, 3,000 joules for the low one. So the higher something is, the higher the potential energy, the ability to do work on something else. Hey, which ball has more potential energy now? They have different masses but the same height. Well, you do your MGH on both. You got a 3,000 to 3,000. They both have the same energy. So it took the same work to lift a 30 kilogram mass 10 meters as it does a 50 kilogram mass 6 meters. They could both do the same damage on crushing something below because they have the same ability to do work on things, or the same energy stored in it. It's not doing anything sitting up there. It's got the potential to do things up there. Alrighty, well, sometimes things can be turned into kinetic energy by doing work on it, or gravity does work changing that potential into kinetic. This is a little bit harder one. Takes a slightly longer derivation to get to. Of the y, it's the 1/2 the mass, and it's the speed squared is the key on this. We could use your kinematics and do some work on that, but this PowerPoint doesn't go into how you find this actual equation. But to find the kinetic energy, it's 1/2 the mass. What people often forget to do is square the velocity. So how much kinetic energy is a 500 kilogram car? That's a really small car. Moving 20 meters per second. Well, it's just 1/2 the mass. So 20 squared is 400. Half of 400 is 200. 200 times 500 is 100,000 joules. That seems like a lot of energy because it is a lot of energy, and it's a very small car. Okay, so we got an apple that falls 7 meters, hits you on the head. What is the apple's change in potential energy during the fall? Then we'll do this Greyhound one. Alrighty, so the apple's just MGH, so it's got 14 joules of energy. It's the 0.2 kilograms times the 9.8 or the 10 times the 7, that's 14 joules. That would be the kinetic energy of the apple after it fell 7 meters, right before it plunked on someone's noggin. Now in the Greyhound, it's 1/2 the mass, 20 times 16 meters per second squared, and you get 2,560 joules. So an interesting question, something to think about, because I don't think this goes into that. If you were to double your speed, or if this dog would run twice as fast, what happens to his kinetic energy? Well, twice as fast, 2 squared is 4. That's 4 times the kinetic energy. That means the dog has to do 4 times the work to get up to that speed. Same idea with your car. It's a lot less work to go from 0 to 30 than it is from 0 to 60 in your car. Because to go from 0 to 60 miles per hour, it's actually 4 times the energy. If you drive twice as fast as you're supposed to, it's not twice the kinetic energy you have, it's actually 4 times the kinetic energy. It takes 4 times the work to stop you. And we'll learn later on that means 4 times the distance to stop you. So it's a much longer stopping distance, but you could do 4 times the damage. Or if you go a little bit over the speed limit, since you're squaring that little bit, that's a lot more energy. That's a lot more damage you could do to another person's vehicle, body, or whatever, ramming into that. So the key thing is, if you double the speed, that's 4 times the energy, not twice the energy. So we have the law of conservation of energy we talked about before. The energy is always there. We're just changing from one form to another form to another form, and we do this in terms of work. Work changes one kind of energy to another kind of energy. This is the first law of thermodynamics. You can't create energy, you can't destroy it, it's always there. That's the happy side of physics. The second law, which we talked a little bit before, is the unhappy side. That's this, even though we're using this, you can't be 100% efficient. This person is not going to get 100% of the kinetic energy out of that as the elastic energy stored into that. Hopefully we'd like to get near that to get a greater energy transfer, but it won't be 100%. So some energy gets converted into thermal energy, which is hard to reuse, which increases the entropy of not just the world, but the universe. Alrighty, so here we got potential energy stored in the spring. It has 10 joules of potential energy. So ideally, you ought to get 10 joules out of the thing. Well, in this case, we only got 8 joules in the kinetic energy. So this spring, elastic stored energy, did 8 joules of work to convert it into kinetic energy. But in the process of converting that into kinetic energy, we lost 2 joules in the heat, which can't be reused. Pop quiz, what's the efficiency of this elastic device into kinetic energy? 30%. Very good, because it's just your 8 divided by the 10. So it's 80% efficient because 80% of the energy you have afterwards is 80% of what you started with. It's the ratio of what you get out to what you put in, and we lost 20% of the 2 joules. Alrighty, so in falling, this is assuming, well, we have a heat loss here. A lot of times we do these problems pretending there's no friction. So how fast would things be moving, or how much energy would they have if there was no friction? Well, this person, if they're falling with 5,000 joules of potential, but they have 5,000 joules of kinetic, that probably means they started out with 10,000 joules of potential energy at the top, meaning they're halfway down. And here they're 3/4 of the way down, and then here they're right at the bottom, right before they hit the mat. It's all in the kinetic energy that was potential right at the top. But the point is, if we were to add up the potential plus the kinetic anywhere here, it all sums up to 10,000 at every single point. That's the law of conservation of energy. So if we assume no heat losses, this is what we end up with, the ideal situation. In reality, it's not completely true. There's some energy loss that you can't get back in reality. But for predicting what things are going to be like, sometimes we pretend there is no drag of the air, that there is no friction or rubbing on things to lose some of that energy. So whatever potential energy we have before and kinetic energy we have before, energy we have before and kinetic energy we have before, we should have the before and afterwards. So we're going to go along the lines, we're going to pretend that there is no loss in heat energy, no air drag, and no friction for a little bit there. Now it turns out when we use this whole law of conservation of energy, we use this to solve for things. Usually the height of something or how high something will go based on your energy to start with, or how fast will that be traveling at some spot given a starting speed. So for a lab, you're going to set up, for a couple point lab, you're going to set up an experiment to find what the theoretical velocity is at a couple different points on your roller coaster like device, as well as the actual speed at the end, and find the efficiency of the whole process. But for the ideal, it turns out we don't have to know the mass. In reality, we do, because there'll be some energy lost in terms of heat. But if we do an ideal situation, it turns out we have the same mass before and afterwards. That all drops out. So it makes it a much easier equation to deal with. So if you know the starting height and the starting velocity, at any particular height, given height, you can find the velocity there. Or if you were to find the velocity somewhere, you could find out what that height would be. Okay, let's do some examples of where you could use this to find heights or velocities. Hey, how about the Mamba? A lot of you have been on the Mamba before. What's fun about the Mamba is you got a big drop, 62 meters, allows the coaster to reach 33 meters per second. That's like 75 miles per hour, so maybe 72, I can't remember. So it's clickety click, 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 clear to the top, and then you got that big drop there. And by the bottom, you're going 33 meters per second. Okay? How fast should it be traveling at the, how fast should it be traveling at the bottom in the absence of air resistance, though? So this is with friction and air resistance, hits the 33. But theoretically, if you drop 62 meters, what should be your speed at the bottom if you don't have any of that stuff? Well, we set this up. So this is your energy before, your height is 62, and your velocity is pretty much about 0 at the top. Maybe not exactly 0, but it's such a small velocity, this is a very small amount that's going to be close enough to 0. Okay, even though if you're barely moving, you're squaring a velocity that you're barely moving is still a very small amount. Okay, so we only have potential energy to start with. Now at the height afterwards, we're going to go clear to the bottom of the loop. So what's the height at the bottom of the loop? 0, so that's going to drop off. So we actually only have this before versus this afterwards, and we're going to solve for that V right there. Okay, so it turns out I don't know the mass of the Mamba. I don't have to for an ideal situation, because the mass just is the same, it drops out. And what else drops out is the kinetic energy at the top and the potential at the bottom, because we went down clear to the height of 0. So now all I have to do is solve for the V. So 2 times the GH, do the square root of 2 times the GH. Whoops, oh, I'm still going to, there's the GH. And then do the square root, 35. So theoretically, that thing should be moving 35 meters per second at the bottom. Dios mio, why is it only going 33? In real life, there is friction. There is some negative work done by the air pushing backwards on the coaster, and friction pushes backwards as well. So both of those together cause it to lose 2 meters per second. And if you wanted to find that energy loss, it's pretty easy. All you do is find the kinetic energy difference. So to find the kinetic energy difference between going 35 and 33, that's the negative work done, or the energy lost due to friction. Alrighty, so we have about a minute and a half to do this problem, and maybe one more, then we'll have to switch to our second video. So here a pool ball is flung off the table this high, and the ball hits the floor at a speed of 6. So somehow they knew it was going 6 when it hit the floor. How fast did it leave the pool table? Well, you set it up just like we talked about. You've got your potential energy at the top, you got your kinetic energy at the top, you got no potential at the bottom, because that's your 0 height, but you do have some kinetic energy, and that's going 6. So 6 goes in for that. The height goes in for the 0.68. We actually don't know the starting velocity leaving the table. It says how fast is it flung off the table. So now you're actually solving for that V. So you can follow and look at this. I'm going to post this, and you can look at it at your own speed. But if you go through and you solve for the V, you find it to be, oh, right on my face. It's 4.7 meters per second by the time you're done solving for this thing. Okay? Example number, this one. We can barely get this in. So you got a 300 kilogram cart going at 8 right there. It's the top of that hill. How fast is it going there at the top of that hill? Well, this will be our first problem on the next video because we have a whole 6 seconds left. So I'll see you in about 2, 1, and